These are very, very quick operations for your CPU to perform. In fact, this is mainly what the CPU does. CPUs don't know how to add numbers together. I've been seeing this video in my YouTube feed for a while now. This algorithm is 1,000,000% faster by this little YouTuber called the Primogen. And I watched it, and it's honestly one of my favorite videos of all time. And I think this is one of the few things that I'm actually qualified to talk about. So I wanted to give kind of my analysis on making an algorithm faster from the perspective of a LeetCode monkey.
1.6 million% faster. It's hard to even display visually because it shows up as nothing. Today, I'm going to show you the 7 steps taken to improve the running time of an algorithm, but here's the kicker. The slowest one was O of n, and the fastest one is still O of n.
So when it comes to interviews, the big O runtime is usually the thing that you want to optimize for. When it comes to competitive programming, though, often like the actual runtime matters as well. And most importantly, when it comes to real development, the actual runtime is the only thing that matters.
Along the way, I'm going to use common optimization techniques that you can use in any application. And then we're going to get a little bit exotic and go into the bit manipulation world to really speed things up. Then, of course, compiler optimizations and SIMD and everything to go blazingly fast. But first, the problem, of course, right? So the problem is simple. It was from Advent of Code 2022, which is find 14 distinct characters in a long string. Once you find 14 distinct characters, you just report the position directly after those.
I'm sure you LeetCode people automatically know how to solve this problem immediately. Given an input string like this, what we want to do is find the first window, which I believe in this case is actually this one, of length 14, so I believe that's this, such that every character in the window is distinct. And then we want to return the index directly after that, which I believe in this example is 19. So how do you solve it? Well, it technically doesn't matter given the fact that this window is of fixed length. If you only care about the big O runtime, it actually doesn't matter. A brute force solution would be big O of, let's say, 14 times n. Obviously, this is a constant. So you check every single window starting at every single character. From the LeetCode perspective, the obvious optimization would be the sliding window algorithm, where we do this. 2 pointers. One pointer is here, left, second pointer is right. You keep shifting the pointer until you get a window of size 14, or you reach a duplicate character. So in this case, we see that our window has 2 J's. Now, how do you detect the fact that we have duplicate characters? The simplest data structure to use would be a hash set, since it does provide constant insertions and constant lookups. Hash sets, though, actually do have overhead, because if you don't know, a hash set under the hood is actually implemented with a dynamic array. So if we want to get rid of the overhead involved with that, we can directly just use a dynamic array. There's actually 2 different ways you could use that dynamic array. One would be, I think, given that the character set is going to be lowercase a through z, you could have one of size 26 where each character will correspond to that index, and maybe it can be a Boolean dynamic array, which tells us if a given character is present in our current window. That way we can continue having the constant lookups and constant insertions. The alternative would actually be to have a dynamic array of size 14, in which case we just take each character, push it to the dynamic array, constant operation. But then how do you perform the lookup? Because you don't necessarily know which position each character is going to be in. Well, doing a linear scan in a dynamic array is going to be an operation like O of 14, still a constant, and that's relatively fast as well. Now, if you've taken my algorithms course, or if you just know how dynamic arrays work in general, they're not magic. A dynamic array encapsulates a static array. More specifically, as the dynamic array grows, it's going to continuously allocate new static arrays to keep up with the size, and they'll get larger and larger. So if we want to remove the overhead from the dynamic array, we could just use the static array from the start. Now, static arrays store data, whether you're talking about a Boolean array or an integer array. So to go even lower, you can use something called a bit mask, which is actually something we covered in the last few LeetCode problems, coincidentally. And so that, suppose you use a 32-bit integer, again, mapping each character to a specific bit. This will be even faster from the CPU perspective because we will be doing binary operations for the most part. For example, bitwise AND, bitwise OR, bitwise XOR. These are very, very quick operations for your CPU to perform. In fact, this is mainly what the CPU does. Believe it or not, CPUs don't know how to add numbers together. They use bitwise operations to do that. And so even though a sliding window algorithm can be implemented with any of these 4 data structures, I hope this makes it clear why the bit mask would be the most optimal way to implement it. And the performance gains definitely are real for large inputs, as we're about to see.
If you're not familiar with Advent of Code, it's kind of like a fun Santa-themed holiday adventure in which you're solving problems to bring Christmas joy. The simplest solution possible would just be to use a hash set, right? Grab the first 14 characters, throw them all in the hash set, and then check the length of the hash set at the end.
Now, one thing I think worth mentioning is the fact that our window here doesn't always have to start at the beginning of the next character. Like if we detected a duplicate, in this case, if we see the second J, we could then start our window after the first J, because we know that the second window is also going to contain 2 Js because it starts at that J.
If it's 14, we got ourselves a go. If it's not, we need to move forward everything and try again. We need to try again, try again, try again, try again. Oh my goodness, look at that. We have found 14 distinct characters. Now all we need to do is report that little J right here, that Jth position, and we've solved Advent of Code. So here's the code. Very, very simple. We simply go.
It's simple code, but this is Rust, so that's not personally a language that I'm familiar with, but conceptually, I think we can see what's going on. It looks like this is going to create an iterable of size 14 given the input, and this second part, W, I believe, is that window itself, and then from that window, we're going to collect all of the elements into a hash set data structure, and then we compute the length of that hash set. If the length is 14, that means it has 14 distinct characters. If not, then there's a duplicate, so it would return false. And to be honest, I'm not sure the semantics of this, but conceptually that's what's going on.
Over 14 characters at a time, collect it all into a hash set, check the length of 14, boom, we're done. Now, there's a very simple optimization that could be made. And this is the first optimization, which will lead us to a 92% faster runtime. And of course, that is to insert characters one at a time. The moment you detect a duplicate, you do not process any further, and we go to the next set of 14. I know.
So that's definitely worth mentioning. And it does fall into the sliding window approach that I talked about. So the optimization he's making is as soon as you detect the duplicate, you don't have to compute a window of size 14, but he's still shifting his window by 1, I believe, when you don't necessarily need to, which I think he covers later on.
I know, it's shocking, right? 92% faster for such a simple if statement. Let's go to the next level of optimization. This is going to improve the running time 8.9-fold, practically an order of magnitude faster, and it's going to surprise you how we do that. That, of course, is to use a vector instead of a hash set. It might be a bit counterintuitive. You're thinking, well, why would checking every position somehow be faster than a hash set lookup? Aren't those constant time? Yes, but so is a single vector lookup. It's also a constant time. But I want you to think about something. When you see big O of 1 constant time, it's kind of a lie in the sense that it's actually big O of a constant multiplied by 1. Now, what is that constant? When it comes to a hash set, that constant is significantly larger than a vector constant. And that should make sense, right? Because when you're talking about a hash set, you have to compute a hash and an index into a large table. Inside that table, you then have to go to that entry and potentially scan through some couple item list if there are any collisions and check for equality. Whereas with
I think he's absolutely right. And I think this is why big O notation can be so misleading for people, especially beginners. The constant does matter. And that's particularly the case when it comes to small input sizes. Now, in this case, since both of them are constant operations, it must be the case that a vector will be faster compared to a hash set because of the overhead. I mean, hash sets are implemented with vectors. It's like how a virtual machine runs on top of your host operating system. You would not expect the virtual machine to be faster than the host operating system. Java code, in theory, will never be faster than C. It'll always be slower.
With the vector, you're still allocating on the heap like a hash set, but you just simply have to follow a reference and calculate an offset into a memory region. That's just gonna be super fast in comparison. And the code's not that much more complex. We create a vector instead of a
Right, so here, the smart thing to do is definitely declare the vector with the capacity up front rather than it potentially like starting out smaller and having to resize. That would be additional overhead that can be avoided. The one thing here, though, that you see is the vector dot contains. So again, this is like O of 14. The alternative would have been to create a vector, I believe, of 26 characters, assuming that the input character set is lowercase a through z. And in that case, we wouldn't need to do a vector contains. And we also would not need to have a vector of characters. We would have a vector of booleans. And for each character, we would know whether it's present or not based on the true or false value.
Hash set, and we simply have to call contains instead of checking the return value of insert. It's really not that much different, but it is significantly faster. And the same code, but in JavaScript, is 6.7 times faster. It works in both languages because adding and checking a list in general is significantly faster than a hash set on a small scale.
Absolutely the case. And fun fact, even on neetcode.io, there are places where I actually do a linear scan through an array rather than using a hash set because it's several orders of magnitude faster because I have a relatively small data set that I'm searching through. So, big O notation is not the end all be all.
Small scale meaning a few items, like 14. All right, the next one should be obvious what we're going to do here, and this one will be 26 times faster, which of course is to use an array instead of a vector. It's stack allocated, and we get like some cache locality kind of benefits here.
Very interesting points. Let's talk about them. From the video the other day, we kind of talked a bit about memory. When a program is running, its code is loaded into memory. We also have a memory region called the stack. It's a fixed size, and we have another region called the heap. When we allocate a data structure within our code, for example, a statically sized data structure like an array, let's say like of size 14, and suppose we do that within a function, well, once that function is finished, this will be popped from the top of the stack. So stack is convenient when it comes to memory because your operating system will maintain like a pointer and it'll tell you exactly where the next variable that you declare is going to go. And after a function is done executing, that pointer will tell you that's the memory that you can free now. Whereas when you have a dynamically sized data structure like a vector, even if you declare the vector up front and you say, well, I'm going to give it size 14. A vector, like I said, is generally implemented with static arrays under the hood, and those need to be dynamically allocated at runtime. And so that's going to use a region of memory called the heap. And your operating system does not have like a pointer that tells you, okay, well, next time I declare a variable, just do it on this portion of the heap. So it needs to actually potentially scan through and find a region of memory where we have enough space to store that. And then once it's time to free that memory, it needs to then go to that region. And there is much more overhead in doing something like this for your operating system than it is to use stack. Now, another term that was mentioned, cache locality, in my humble opinion, and I could be wrong about this, I don't believe that would be the most significant factor when it comes to the speed up of using an array rather than a vector, because cache locality basically means when you read, suppose 1 byte or maybe 4 bytes, one piece of data from memory, your CPU will actually make an assumption and say that, well, if you're reading memory from there, I'm going to read extra memory close to there and store it in the cache because it's a quick operation for it to do. And if the assumption is correct that you are going to need the data near there, well, then it's been cached. Now, that would mainly become relevant if you had a vector that was continuously growing and continuously being resized, because every time you resize a vector, it's potentially going to deallocate some memory from the heap and then allocate new memory in a different location in the heap, which is probably going to be of larger size. And therefore, the CPU is once again going to have to take all that data and cache it again, whereas a static array stays fixed and that data will probably stay within the cache and there's no resizing going on. I believe for a relatively small vector, though, the cache locality wouldn't be significant. Again, I could be wrong. If you know more than me about this, feel free to comment.
Much, much faster. But obviously this one's a bit more work because now I have to keep track of the index as well, because I don't want to keep checking all 14 elements every single time, but just a subset of them. But still, not much more complicated than our previous solution. Now, I know at this point this has all been a bit surprising, especially if you have not used a real language meaning a language that has static arrays. Hey, sorry, JavaScript! What about array buffer? Oh,
based on that definition, I think Python is actually also not a real language, which, I have no complaints about.
Okay, calm down. I mean, they kind of do. But real talk, these next couple of optimizations are going to be a bit wild. We're going to go from 26x to 233 times faster. We're starting to get into the blazingly faster category. All right, before we can go blazingly faster, which is technically a word, you first need to hit the subscribe button, and I'm going to explain to you about bits. Because from here on out, all the solution involves some bit manipulation to gain some super speeds, because we no longer need to use an array. We can use a singular 32-bit number to store the state of our search. One thing you have to understand about ASCII characters is that there is a numeric value associated for each one of them, and they happen to be contiguous from 97 to 122. Second, a U32 is an unsigned number that has 32 bits. You can think of that as an array that has the ability to store a true or a false in 32 positions. A true being a 1, a false being a 0. That means
Right, so what he's getting at here is that a single integer can be used as a replacement for the hash set or vector, given that we can create a unique mapping for each character to a specific bit. The only complexity involved with this would be coding it up. So from our perspective as programmers, the solution might be more complicated, unless of course, you're a leet code person like me solving all these bit mask problems lately. But from the CPU's perspective, this is going to be a much simpler solution. It's going to involve less instructions.
Means any character that's moduloed by 32 will result in a number between 0 to 31, which is how many.
So this is a very interesting way of doing it. I actually do it a different way. I typically get the ASCII value of the character. Let's say the arbitrary character is X, and then I subtract from it the ASCII value of lowercase a. This is generally a built-in function. In Python it is. In a language like C, I'm not 100% sure about Rust, but in C, a character is generally a 1 byte value or 8 bits. In C, you don't even need, I believe, a built-in function to do this arithmetic, because you can take the subtraction, you can take a character, and when you do the subtraction from it, for example, if you were to do lowercase z subtracted by lowercase a, implicitly the integer values of each character will be used. So basically the approach that I'm suggesting would map each character from 0 to 25 in a straightforward way. Now, the approach he suggested is actually very interesting. You take that integer and actually mod it by 32. The reason for the mod by 32 is because we guarantee that every character will be mapped to a different position, given that this set is like 25. If it was greater than 32, that guarantee would not be true. But the difference, though, is that modding by 32 guarantees that the output will be somewhere between 0 to 31. That's fine because we have a 32-bit integer, so each character will correspond to a distinct bit in our 32-bit integer, but we don't necessarily know that the order of these would hold. I believe this modded by 32 is going to be 1, this would be 2, and then this would end up being 26. So coincidentally, it does work out to be pretty similar, and I'm actually not sure if that's a coincidence. Maybe these ASCII values were set intentionally so that modding them by 32 would produce this, though I could be wrong.
How many bits are stored in a U32? Let's go over a quick example. Let's say our search state is 0. We have not seen any characters yet, and we want to insert the character D. D, or 100 modulo 32, is 4. A left shift operator is the equivalent of multiplying by 10. That means we're going to shift this 1 over.
The terminology he's using, I'm not familiar with using like base 10 terminology when referring to binary numbers, but maybe that is common in some cases. But just to make it clear, we are dealing with binary here. When shifting to the left by 1, we are actually multiplying the underlying integer by 2. And lowercase d, if this is the binary representation of it, that's actually the integer 4.
Or by 4 positions, thus equaling the binary representation of 10000, or binary 10,000. So if our state is equal to 0 and we OR it with our new binary value that we just created, the resulting value will be binary 10,000.
So just to make this clear, if we have, let's say, an empty 32-bit integer or 0, and we want to set a particular bit, if we had that mapping, suppose A corresponds to 0, suppose B corresponds to 1, and suppose we want to set B, we want in our data structure, which is now no longer a hash set, it is a bit mask, a 32-bit integer, we want to then say this bit should turn into a 1. And with that, we can take 1, bit shift it to the left by this number. I'll use actually example D. In this case, D would correspond to 3. So we would take 1, shift it to the left by 3. So it would go from looking like this to looking like this. So that tells us this is the bit we want to set. And then you can take this number, put it over here, stack it here, and then do the bitwise OR between these, which will set the bit to 1 here, and every other bit will stay the same. From your perspective, if you're a beginner to bit manipulation, this seems complicated. It is. For most people, this code wouldn't be as readable as the hash set solution, but from your CPU's perspective, this is actually more readable. Your CPU understands this more easily because there are less instructions involved. So this is a extremely interesting solution to me, and it's actually very subtle. So I think it's definitely worth talking about this one because it's the first one that actually takes advantage of the fact that we don't always have to restart our window from scratch every single time. And it does it in a pretty clever way. Suppose with the and or operations we talked about, you check a window, you set each character, and if you see that a character is already set, well, at that point, the window can't be correct. So you try the next window. And we do it from scratch. Now, if we use actually the exclusive OR operator, which if a bit is already set, it will flip it. A 0 will turn into a 1 will turn into a 0. That's interesting because given the first window, suppose, we can then take a new character and then flip the bit. So if it was 0, that bit will end up being 1. If the bit was already set though, it will turn into a 0. That indicates to us that we have duplicate characters. Now, if the bit mask originally was meant to store that this particular character exists, but now it's 0, that seems like a conflict. It seems like the bit mask has lost meaning. But remember that the purpose of the bit mask is to count, are there 14 bits set? Because if there are, that means there are 14 distinct characters. So the fact that duplicate characters will turn a bit into 0 actually doesn't cause any issues. And even more so, now we can actually shift our window by 1 every single time. We can take the leftmost character and exclusive OR it to toggle that bit. And we can take the rightmost character and also exclusive OR it to toggle that bit.
Go over the input 14 at a time. If you're not familiar with the Windows operation, it literally goes from 0 to 13, 1 to 14, 2 to 15. It just does a nice window for you. And we keep doing that little window crawl motion over. This clever algorithm earned Benny 233 times faster than the hash set, or
and for the record, just the window aspect of that solution is clever, but the XOR is really the complicated part of that solution. You might look at it initially and think you understand it, but I don't think it's actually as trivial as that.
Or 23,000% faster. It is incredibly clever algorithm. Hats off to Benny. Damn it, Benny. What a smart man. And to think my solution was only like 100x faster than the hash set one. I feel so stupid looking at Benny's super clever window crawling solution. Let's kind of get into our final form here. We're going to look at the algorithm that sped up Benny's by over 4-fold. It was approximately 1,000x faster. So instead of walking through the idea, let's just walk through the code on this last one because it's just mind-blowing. So the first thing we do is just start by going through a fixed size windowing right here. You'll notice that we do a input get from index to index plus 14. So that is a constant size window. It's very important to remember that. Next, we create a state variable, 32 bits, just like Benny's solution. Next, we're going to go through that slice and we're going to iterate in reverse. Now, for me personally, when I saw this, that means we had to take an iterator, get all of the elements, collect them all up, and then walk backwards through them. I thought there's no way this is faster than Benny's. We do the same operation. We take the modulo 32 of the bit. We test to see, is that bit already set to 1? If it is set to 1, then we found a place of a duplicate. We then shift on that bit using the OR operator. Then we return whether or not...
Okay, I thought that this was something clever going on, but no, it's actually just set the bit and determine if it was already set and then return the result of that. So even if it was already set, we would still end up executing this line of code, which wouldn't really do anything if it was already set.
We've seen this byte already. So here's one of the two mind-blowing optimizations. If we have seen this byte, Since we're going backwards through the list, we can actually jump all the way to this position +1. That is.
Let's think about that for a second. What the Primogen just described is actually very simple conceptually. It's similar to what I talked about earlier. Remember, let's say we're still dealing with like the 14 fixed size window. We read from left to right, we see there's a J and we see there's a second J. So where would we want to shift our window next? Well, the next window can immediately start from here, because this window is still going to have duplicate J's. Now, the clever thing for this window, iterating from right to left, is the fact that there could be more than just 2 duplicates within the window. Notice that if we went left to right, this is what the window would have ended up being. Now, if we go from right to left, we see this J and then we see this second J. So in this case, we will see that, okay, that second J can be skipped. Start the next window 1 plus the position of that. So this one will actually start a couple positions further to the right. Now imagine if this window was like all J's. The first window would have ended up just being shifted by 1 like this. The second window, if we had like 2 J's here, the second window would have been like this. So that's the difference. Like all this section is what we ended up skipping. And if you consider that each one of these positions corresponds to a window of size 14, the optimization is actually pretty significant. That's actually something I did not consider. I don't know if any of you super leak code monkeys in the chat thought of this one. I didn't, because I usually consider big O runtimes, and this doesn't really affect the big O runtime, but it's a very significant optimization. Anyways, I just thought that was worth explaining because I think those kind of minor details can get lost in the sauce. And this is not trivial stuff. Even for me, this is not trivial.
Is a huge optimization. We're going to cut out several characters we don't have to look over and over again for. If we do not find a repeat character or the false condition, we actually return this index, which is correct. This is the position of the 14 contiguous characters. Now you're probably asking yourself, how? Show me how this was so fast, because I don't understand why going backwards through a list was faster other than that little jump. But you still have to iterate over everything, right? Right? So check this out. This is the Compiler Explorer. This is godbolt.org. So first I put in Benny's solution right here so we can look at it first. Now, the first thing that you'll notice is that the input right here, since it was a fixed size, what did the compiler do over here during optimization? It actually unrolled the loop. It just made it all in line. So there's no jumping back and doing this a whole bunch and then jumping out at the end. Then we get to this, our Windows 14. Now this is kind of interesting because this is pretty much the primary loop right here. We just go over this code over and over.
While this is very helpful, like this kind of gives you insights into how the program is executing, I think the intuition that I gave is honestly for a human more understandable. I think, these tools are great. And I think this is kind of a point. I wonder how ChatGPT would explain what I just kind of said. Like I mentioned, it's a very subtle point.
And over again. So it's pretty fast, right? But now let's look at David's solution. So we have the same thing happens to David's solution right here. It actually gets unwound. So that reverse iterator happens in reverse right here. You can see it right there. Look at that. 11, 10, 9, 8, 7, 5, 3, 2, 1, and then whatever this means. I don't even know what it means. And I have been told that what's happening up here is all the SIMD stuff that's happening. That means single instruction is multiple data calculations in a single go with the compiler. That means you can massively speed up what you're doing. So not only is the inner loop being unrolled, unlike Benny's, it's also getting SIMD optimization. And that, my friends, is blazingly fast. But you're probably asking yourself, wait, that one?
So now I think we're getting to a point where this stuff is going to be beyond me, because I think we're getting into operating systems and compiler optimizations. But it's always fun learning.
One was 16,000 times faster?
No.
That was just shy of 3 orders of magnitude faster. 1,000x faster is 983x faster. So how did we make it that much more faster? Of course, I just used my 64 threads that are just doing nothing. Come on, of course I'm going to do that. And that allowed us to go blazingly fast.
Okay, he got us there. I actually didn't watch this entire video before I started reacting to this. I wasn't expecting that one. You got me, Prime.
In fact, 16,000 times faster.
Let's take a closer look at that. So the base solution was 1. So David's solution is about 1,000 times faster. And so he went from 1,000x to 16,000x via like hardware improvements. Well, not just hardware improvements, but making the code parallel. And it looks like David's solution, the one that went in reverse order for each window, and also kind of did the sliding window optimization, was about 4 times faster than Benny's solution. But it looks like the easiest performance gains just came from the fact that we were using better data structures with less overhead. So while these solutions are less readable and more difficult to come up with, I think these are very manageable. By the way, if you're interested in this kind of stuff and you want to learn more, or if you're just preparing for like coding interviews and stuff, you might be interested in neatcode.io. It has a ton of courses, adding a lot more lately. And if you want to implement like a dynamic array, you can actually do that for free, 100% free. If you just go to neatcode.io, it's this nice little LeetCode style environment. You can learn how dynamic arrays are implemented under the hood. And I really enjoy stuff like this. If you guys know of any more videos like these, please send them my way. I love this stuff.